Thank you all for coming yesterday and for coming out today. We have another great day of speakers and very excited to start off this morning with Gitta Kutyniok, who is a professor at LMU Munich. She is very well known for her work, pioneering work in harmonic analysis and compressed sensing. And we're extremely excited to have her here and to be able to talk to us. I'll not take up too much more of your time. Take it away.
Yeah, thank you so much for the invitation and also very nice introduction. Let me start by sharing my screen. Okay, yeah, again, I mean, thanks a lot for the invitation. It's certainly a great pleasure and also great honor for me to give a talk here in deep math. I think we all know how tremendously successful deep neural networks are these days, but we also know at the same time that there is a huge lack of theoretical understanding, in some sense, the mystery, why neural networks work that well. And so in this regime, there are several directions of research people pursue. And one of the, let's say, great mysteries is why neural networks generalize that well, in particular in the high parameterized regime. And so this is what I would like to focus on in this talk. In the case of spectral graph convolutional neural networks, I will show that in a certain sense, those networks actually do generalize, and we can also theoretically prove this. Yeah, I mean, we all know that neural networks are currently around us and will be so also much more in the future. I mean, we can think of self-driving cars, surveillance tasks, legal issues. So in the States, I mean, I became aware that their job applications are sometimes already pre-screened by neural networks, and then the whole healthcare sector where not only imaging modalities use neural networks, but also if critical decisions need to be reached. And so we see, I mean, there are a lot of really sensitive applications where we need, in some sense, security and robustness of neural networks. But from a theoretical side, I mean, there is still a great lack of understanding. A lot of people are pursuing this direction currently, but at this point, I think we can say that there's no comprehensive theory to understand fully why neural networks work that well. What I find interesting is that the current trend is also to combine neural networks or deep learning with mathematical models, in particular in applications like inverse problems or also concerning partial differential equations. So to go with modeling as far as it is reliable and then combine it with neural networks in some sense to optimally balance both worlds. Still, from the neural network side, I mean, there's this lack of theory. So also if we combine it with physical models, we need to pursue to derive a theoretical understanding, to also understand these hybrid methods in depth. So let's enter mathematics of deep learning to set a bit also the notation. So what is a neural network? It's a very mathematical object. It's combined out of affine linear maps and activation functions. So we apply an affine linear map, ax plus b, to some x. Then afterwards, we apply an activation function, which is typically a nonlinear, which we apply component-wise. It's a univariate function. And then afterwards, we apply another affine linear map and so on. And so this gives me a function from some Rd to Rnl, where usually or often NL is equal to 1. And this is typically depicted in this way, where we have here the entrance neurons, we have here the combinations mimicking the first affine linear map, then the activation functions, and so on. Now, how do neural networks operate? And I think we are all aware of this, but from this we can deduce which theoretical directions are of particular relevance and which need to be pursued. So a very high level setup is as follows. We have a very complicated function in the background, maybe defined on some lower dimensional manifold, where on one hand we have one type of images, for instance, on the other hand another type of images which we want to classify, and what we have at hand are sample values. The first step is then to select an architecture of a neural network, and already at this point we run into some problems because it's not clear initially how we choose the number of layers, how many neurons in each layer, and so on. And maybe we also don't want to have a fully connected network, but we have certain entries in the matrices which we want to set to equal to 0. That means we already pre-select certain connections beforehand. Once we have decided upon the architecture, then the next step is to learn the network, meaning we to learn the F1 linear functions, so the matrices and the biases. This is done by an optimization problem where we aim for the following, that the function values, so the labels, which we know are close to the evaluation of the neural network in these samples, and closeness is given by a loss function. Sometimes you might want to put additional constraints on, let's say, the weights and the biases. This is done by a regularization term, and then we minimize. This we usually do by stochastic gradient descent, giving us a network which we hope is then close to my initial F. So, and from my perspective, let's say some of the main theoretical directions and question areas arise. The first being expressivity, which is the question which architecture to actually choose. So questions which are studied in this range are, I have a network architecture, how powerful is it? Can it actually represent or approximate the correct functions? This requires a lot of applied harmonic analysis, approximation theory, tasks like this. Then learning. I have my learning algorithm, does it converge? What are good starting values? So these are questions which require areas like optimal control, optimization. Then generalization. I train on training data set. Does it generalize? Does the network generalize also to test data? For instance, what impact has the depth? So this requires learning theory, statistics. And so these three areas are exactly the three directions which are present in statistical learning theory: the approximation error, the error from the algorithm, and the sampling error. And then there's another area which I find personally also quite exciting: interpretability. We have a fixed neural network. Can we deduce how it reaches decisions? And so from a mathematical perspective, I think, the most explored area is the area of expressivity, which was already very well studied for shallow neural networks. So when there was a first wave of neural networks, learning a bit less, and generalization is still, a reasonably open area. And this is a very new area where, to my mind, also a lot of mathematics still need to be developed. And so in this talk, I will focus on this area of, as I said, of generalization. So what is generalization? Well, there's a key observation, which in some sense is the following. If I have a deep neural network, so I have a network with a huge amount of parameters, then there's a surprisingly small difference between the training and then later on also the test performance. So these networks, if I have really an over-parameterized network, then these networks seem to generalize very well. Yeah, so therefore sometimes if you talk to practitioners, that was my experience, they say which network to choose. Well, just choose the largest which fits in your GPU. And so intuitive reasons could be, well, there could be properties of the architecture, maybe some regularization techniques used during training, but in some sense, all of those more intuitive reasons do not really unravel the true mystery why these networks generalize that well. And so to make it a bit more precise, what we mean in this regime, there's the famous double descent curve, which is not completely understood yet. So this is what is understood in some sense from classical statistic learning theory. So here I have my capacity of the hypothesis class, meaning if I are in the neural network setting, these are the neural networks with a larger and larger number of parameters. This is the error. And so the training risk certainly converges to 0, but the test risk at some point converges again. In a way, the test risk grows from some point on when I get into the overfitting regime. Now, the mystery of neural networks is that actually at this point now, if I let the neural network grow even further, the capacity I let go to infinity, then at some point the test risk goes down again. And so to understand this phenomenon, there are various approaches these days. Certainly, I mean, the old tools were BC dimensions and Rademacher complexity, uniform stability, and neural tension kernel, and so on. And there is a long list of papers which, and you see, I mean, research accelerates, which goes in this direction and tries to understand in particular why this double descent curve appears. So in this talk, as I said, we want to focus on graph convolutional neural networks. And in this world, there's a certain type of generalization phenomena which actually does not appear in normal convolutional neural networks. And this is what this talk will be about and what I would like to discuss with you. And the work I present is joined with several collaborators. There is my postdoc, Ron Levy, who is right now still at TU Berlin, but soon also joining me at LMU Munich. Then two students from Wai Huang and Lorenzo Bucci from Italy, and Michael Braunstein from the Imperial College London. Yeah, graph convolutional neural networks. I mean, what is a graph convolutional neural network? Well, it operates on graph signals. So I have a signal which is defined on the graph nodes and goes, let's say, to some RC. And then the graph convolutional neural network takes this graph signal. It applies a certain convolution, which we will discuss, then an activation function, pooling, and so on, like a normal convolutional neural network. And in general, one can say graph convolutional neural networks do generalize classical convolutional neural networks to signal over graphs domain. Why generalize? Well, I mean, if you're in the very special case that the graph nodes are in some sense just in one line, I mean, then this is the normal case that you are in Rn. Graph convolutional neural networks are extremely popular. There are tons of applications where they are used these days. I mean, there are recommender systems where, for instance, people vote or inform about how they like certain movies, and then you would like to suggest other movies to them. So this would be the classical Netflix problem, but also this is something much more generality. Then fake news detection, where you have networks and you would like to detect where fake news are, how they distribute. And also in very different areas, like for instance, chemistry, where the molecules are of a graph structure, and then you would like to analyze those, maybe classify them under certain constraints. So these are graph convolutional neural networks. We will go in more detail in a bit in a moment. And certainly generalization is desirable also here in this general setting. So it is desirable that these graph convolutional networks should generalize to graphs and signals unseen in the training set. So now here we have a bit different situation, or more general situation as before. Remember before, when we are in the Euclidean setting, I mean, we have entries like, for instance, in Rn, and then we have different training data and then also test data. Here, we also might have different graphs to which the graph convolutional neural network is applied to. Different types of graphs, and then, as you see here, different values to each of the nodes. Yeah, so there are two distinctions. Not only do we have somehow different values, but we also apply the network to different graphs. And so this creates now an additional question concerning generalization ability. This is the concept of transferability. And so this is the following problem. I have two graphs. Yeah, so you see these two graphs here. And these two graphs, let's assume they model the same phenomenon. How we define this, I mean, I will also be more precise later on. So I have two graphs which model in some sense the same phenomena. As you also see here, you have here two different, let's say, balls and one small connection between those. Then what you would like is certainly that the graph convolutional network, or these filters, should have the same repercussion on both graphs. And it could be that in the training data set, maybe only one type of graph appears, and then the test data contains a graph of this type. And certainly you would like then the network to generalize to this graph. And what we will show is transferability for spectral graph filters, spectral graph convolutional networks, which is a certain type of filters, again, which we will discuss. Yeah, so you see, I mean, this is, let's say, not the full generalization question, but this is a certain aspect of it, which appears in the question, in the setting of graph convolutional neural networks. So what are graph convolutional neural networks? Well, I mean, the activation function is again applied component-wise. Pooling is done via graph coarsening. So here I have the graph, I have a certain algorithm to coarsen it. That's how pooling is applied. What about convolution? Well, I mean, there are two different, let's say, strategies one can pursue. There is a spatial approach and a spectral approach. So the spatial approach, the spatial convolutional approach does the following. So I have, let's say, a window which tells me if how, let's say, to aggregate features from the neighboring graphs, from the neighboring nodes to this one node. So how, let's say, to get a linear combination, compute a linear combination for, let's say, the node I'm considering, and then I slide this window over the whole graph. So that's the spatial approach. Everything happens in the spatial domain. Then there's a spectral approach, which uses, as we know from Euclidean theory, the convolutional theory. So this we define in the frequency domain, and then in frequency domain we multiply by a filter, and then we bring it back to spatial domain. And for a long time it was believed that spatial graph convolutional networks, or spatially defined filters, that they are transferable, but spectral are not. And so what we will show in this talk is that, in fact, also spectral graph convolutional networks exhibit transferability. And one should say, I mean, also for spatial ones, it's not proven, it's just strongly believed. But here we'll see that also for spectral one, we can actually analyze it, and here we can get very rigorous estimates how good the transferability property is. Okay, so let's now talk about spectral filtering. Okay, so let's start very basic. I mean, we all know, I guess, what a graph is. So you have you have vertices, you have edges between those, you have an adjacency matrix, which is built from the connections between each pair, or between each pair of nodes, and then we have the so-called degree matrix, which for each node, it in some sense sums over the connections, the weights of the connections to this node. Using this, we can define a graph Laplacian, which is just the degree matrix minus the adjacency matrix. That's the unnormalized graph Laplacian, and then we can also normalize it. Now, this is this nice operator. It's a self-adjoint operator, and we have eigenvalues, we have eigenvectors. Eigenvalues correspond to frequencies, eigenvectors to free modes in a sense. And so the idea of this graph Laplacian is that it shows and exhibits the geometry of the graph, and what you see here are the first graph Laplacians of such a graph, which is like a dump shell. And you see here, indeed, I mean, the frequencies, in some sense, here's a low frequency, and this would be then higher frequencies, which are also adjusted to the geometry of the graph. Now, how does it correspond to frequencies and free modes? If we go to, let's say, a more well-known setting, the Euclidean setting, then the Laplacian there is just minus the second derivative. So here I have eigenvalues, and these are, in this setting, the eigenvectors. And so this way I then get also a Euclidean spectral filtering by using these Laplacian eigenvalues and vectors. Okay, so now I have this graph Laplacian. It kind of encapsulates the geometry of the graph, and now I'm wondering how to define convolution. So let's assume I have a graph Laplacian. I have a particular graph, Laplacian, I have a particular graph Laplacian, and I denote the eigenvectors by uj. Then if I have on my graph a signal, which I now call f, then the convolution of that is defined in this way. So these are the filter coefficients, these Cj, and here I have the eigenvectors. And so this would be my convolution, how I compute it, and I choose then the filters and would learn the filters during the learning process. This has certain disadvantages. Well, why? First of all, it's computationally demanding. I mean, you need to compute here always the eigen decomposition, which takes a long time. Also, I mean, there's no fast Fourier transform for graphs, which creates another problem. So if you want to compute something in the Fourier domain, you actually have a problem. But maybe even worse, this is not transferable. Because you see, the problem is as follows. If you now have a small perturbation, I mean, then these might perturb even more significant. And even if they perturb very small, I mean, then you have here these fixed filters. So that could lead to something very different after the filtering process. Yeah, so if you have a fixed filter, then this can have very different repercussions on quite similar graphs. So if you perturb slightly, I mean, this completely hits through and might change this radically. That's a problem. So the solution for this is going a bit deeper into functional analysis and using what's called functional calculus and defining the convolution that way. So in a nutshell, what is functional calculus? Again, I mean, let's assume we have a self-adjoint operator. This will be later on our graph Laplacian, which we are already familiar with. Now, let's assume this operator has this shape. So here I have my eigenvectors and here I have my eigenvalues. Now, what functional calculus does is something quite nice. It tells us if I have a function, then it defines what this function does on an operator. So it allows basically to apply a function to an operator. So it gives me a meaning of what g of capital T is. This will be another operator, but it gives a precise meaning to it. So for instance, if g is the square function, this would be t squared. But it could be also something very complicated. But in any case, the decomposition, which we had here, then looks as follows. And you see the nice thing is that the eigenvalues remain the same, but here now the eigenvectors, the eigenvalues change this way. And in particularly nice is for let's say, simple functions, like for instance, rational functions, we can write exactly down what g of t is. So if g of lambda is a rational function like this, then g of t, we can calculate exactly in this way. Yeah, so we can exactly write it down, meaning I don't even need the eigenvectors for it. Okay, so now what we do is we use this functional calculus and define the filters this way. Now remember, this was what we did before. So I have here my filter coefficients. Now instead, what I do my filter is given by a function. So here the filter is given by these discrete values, and now my filter is a function. And so how do I apply my filter to this graph signal f? Well, I apply the function to the graph Laplacian, and then I apply this operator to f. And this translates to this formula. So what advantages does it have? Well, I mean, it actually solves the instability problem, because now if I change my graph slightly, then these UJs might change, but the eigenvalues will change in a similar way. So this basically compensates for changing in here, and therefore this remains stable. Moreover, it also solves the computational problem, because we said before, I mean, there's no fast Fourier transform on graphs, and also it's quite time consuming, sometimes even not possible for massive graphs to compute the eigen vectors of the graph Laplacian. But here we can actually circumvent this problem, because if G is a rational function, then if I go back one slide, then I can write down G of t precisely. Yeah, so then I don't even need to compute it, I can write it down exactly. Yeah, so just keep in mind, instead of having now here the filter coefficients, my filter are now functions. Okay. Okay, so now let's approach our problem transferability. And for this, certainly, I mean, we first need to talk about what we precisely mean by transferability. Still, we have, let's say, a more vague, intuitive understanding of what it means. Okay, so this is what we want to put into our network, weighted graphs. So a weighted graph, what is it? Well, we have points, and then we have, in some sense, the weights, which give us, let's say, the strength of correspondence between pairs of points. Now, there's another, let's say, structure which exhibits something similar, and which is a continuous structure. So these are metric spaces. So metric spaces consist of points and distances. And what we will do now is we will view graphs as a discretization of metric spaces. In the following sense, you see, I mean, here for weighted graphs, I have the weights between 2 points, and for metric spaces, I have distances. And so now the correspondence will be, if the distance grows, then the weight goes down. So the weight gives us, in some sense, the meaning of the distance between 2 points. And this seems to be very natural. So how we define graphs which mimic the same phenomena is that they are discretizations of the same metric space. So we have, in some sense, a continuous function structure, continuous, which overlays it. And then underneath, we have different discretizations. Okay. And basically what we will now do is in this figure. So these are 2 graphs which in some sense mimic the same phenomena. They come from the same metric space. And let's assume, so this metric space is now M, let's assume I have a signal on it. This signal I now call here F. Yeah, so this is my signal on the continuous structure. Now I would like to compare or analyze transferability. So what do? First, I need to bring my signal down to both graphs. This I do by sampling. So the operator will be later on always denoted by capital S. I bring that onto both graphs. Then I will apply the same filter. So what does it mean? Well, I will apply the same function. And now certainly, since I have different graph Laplacians, I apply the same function to different graph Laplacians. Yeah, so this was my filter. So if I go back, so let me go back so that it becomes clear. Yeah, so you see here, so this is my filter. And if I have different graphs, I just need to apply it to different graph Laplacians. Okay. Okay, so now I have the filtered signal on both graphs, filtered according to the structure of the graph. And now I bring it back up by, let's say, some reconstruction operator, which in each case brings things from the graph, from the 2 different graphs up to the same metric space. And then I can compare it on the metric space on the continuous level. And so the difference here gives me then the difference in repercussion of that filter on the 2 different graphs. And so this I would like to analyze and, let's say, bound. And certainly then not for each filter, but I mean for the whole network. Okay, so let's define some notation, which we already saw on the previous slide. We have an analog domain with the Laplacian. We have our graphs with the graph Laplacian. We look at so-called Parley-Wiener spaces, which are band-limited spaces corresponding to the graph Laplacian. So these are functions on the Borel space M. So Pauli-Wiener space will be always denoted by this way, and lambda will be the way it is band limited. The band is lambda, the eigenvalue lambda. So the sampling operator, as we said, brought things from M up to the graph. And then I have the other operator, which again, or down to the graph, sorry, and then I bring things back up by this interpolation operator or reconstruction operator. So this goes back from the graph to the continuous structure above. And this is what we would like to bound. Just if we have just one filter, we have a signal S, which we call now S. We bring it down on the graph, we filter it, we bring it back up, and we compare it first just to the following. If I have my filter, if I have my signal, and then I filter it only on the continuous setting. Yeah, so this is just if I have just have one graph for now. Later on, I compare it with a different graph. But this is in some sense the first estimate I need. I compare things on the graph, if I apply the filter on the graph, compared to if I just work in the continuous space, and then this way I can also compare it to a different graph. And in the estimate, one component will be the transferability error of the Laplacian. So you see here, this is just the same, only now my filter is just the identity in a sense. So I bring it down on the graph, I apply the graph Laplacian and bring it back up, and here I just apply the Laplacian. And another component of the error will be the consistency error, which is my sampling reconstruction strategy. How close is it to the identity? And so this is the first result. You see what I just explained on the previous slide is written. You see the components here. So this is the transferability, the error, the transferability of the filter. So I have my signal in this Pauli-Wiener space. I bring it on the graph, I filter it, I bring it back up, and I compare it to what happens if I just leave everything on the continuous setting. And the estimates which I get, the first component is exactly the transferability of the Laplacian. So here I have G just being the identity, and here this is the consistency error. And so I have the components here in front. And this is if this is on the operator setting, and this is if I apply it to a certain function. So the essence of what we see here is written down in this last line. So the transferability of the filter can be estimated by the transferability of the Laplacian and the consistency error. And so this result, holds actually in, or can be applied in various different settings. What we saw is the setting where you have here a Borel space, S is a sampled graph, and then you have sampling and interpolation. But it can be also applied to different settings where M is a, let's say, a very fine graph. G is then a coarsened graph. S would be then coarsening by averaging, and bringing back up would be piecewise constant interpolation. Or M could be a graph. This could be a perturbed graph. And then the sampling procedure would be the identity and also the reconstruction. But certainly, I said, we also need to look, and this is then the general setting, which we need to analyze. What happens now if I have a graph convolutional neural networks here with ReLU filters? With ReLU activation functions, with Lipschitz filters, I have two graphs, and accordingly two graph Laplacians. And let's say these come from the same metric space. And so what I now need to analyze is, I need to analyze what happens if I put this graph in my neural network and I pass it through now all layers. And certainly the previous estimate, which I showed you, will become important. And so this is what is written here. You see, I mean, this is the transferability of the Laplacian, and this is the consistency error for each layer L. And so this is what we assume can be estimated by some delta. And if this is true, I can now estimate the transferability error of such a spectral graph convolutional neural network. And the estimate is given in this way. You see the components here. This is the delta, which comes in some sense from the transferability of each filter in each layer. You see here the number of layers, the dimension of the Pauli-Wiener space, and the D comes from the Lipschitz constant of the filters. So this gives us an estimate now for the transferability of spectral graph convolutional neural networks. So this is the estimate which we get. The transferability is in some sense bounded by the transferability of the Laplacian and the consistency error. Now, the question is, I mean, the consistency error, I think one can imagine that this one can make small, or this depends also on the structure of the graph. We have our hand on that. But the transferability of the Laplacian is maybe a bit more doubtful. And so what one can prove in this regime is the following result. If I have, let's say, again, a metric space M, and if my graphs are constructed from random points in M, so I bring in randomness here in the game, then the graph Laplacians approximate the same continuous graph Laplacian with higher probability. So then this transferability error I can make small. So this is one statement that indeed it is possible that this is small, but certainly, I mean, this depends each time on the situation one is in. Okay, so let's think about transferability again a bit for a moment, because transferability can now appear in certain different ways. So first of all, there is what one could call concept-based transferability. So we have a training set with a variety of different graphs, which also mimics the same phenomena. And then via training, the network should learn somehow the concept. So it should see maybe the same phenomena in different graphs, and then it learns how to transfer to different graphs. And then if there's a new graph which mimics the same phenomena, it might have learned this ability. And then there's the other transferability, which is principal transferability. So there I just have a single graph training set, and the network just saw during the training phase just this one graph. From one phenomena, there's just one type of graph. And then, well, I mean, the network didn't learn somehow how to transfer it. It needs to rely on that there is some built-in capability for transferring. And so this is what we studied with our estimates. So this is a built-in capability of spectral graph convolutional networks, which requires no training. And so the success of these spectral graph convolutional networks relies indeed on both types of transferability. Okay, so let's finally look at some examples. To, in particular, analyze this principle via concept-based transferability. So for doing that, we need to isolate the principal transferability from the other one. So how do we do that? Well, we just take a single graph and test it then on other graphs. So here we do it in the area of imaging sciences. So we have an image of a certain fixed resolution. So the network only saw that resolution, and then the question is whether it can also deal with other resolutions. So here my network, my graph is a grid, And the other networks, the other graphs are then just finer grids. And what you see here is that the spectral graphs, so these are two graph convolutional networks, one spectral based, the other spatial based. And what you see here is that the spectral graph behaves in a much better way than the spatial graph convolutional network. So here this is somehow showing that spectral graph convolutional networks indeed have a better, let's say, ability for principal transferability. The second example comes from citation database. So here we now compare the Laplacian transferability with the filter transferability. Here the low pass and the high pass filter. This is, in some sense, the theoretical bound, and what we see is that the examples indeed obey our theoretical bound, which is expected. I mean, some are close. I mean, it's not always sharp, which cannot be expected, but they obey very closely the theoretical estimate which we derived. And so here we study graph perturbations. This was another point which I made before, so we can also analyze perturbations of graphs concerning transferability properties. And again, here the Laplacian error is studied via versus the filter error. We see that there's again a linear here, quite precise linear relationship with different filters, low, high, and mid-pass filters. So here our graph perturbation correspond to randomly removing edges, and we have this linear relationship, or we can randomly add edges. So this is another type of graph perturbation, or we can also randomly remove vertices. And each time we have this more or less linear relationship. Okay, so let me come to some conclusions. So graph convolutional networks are a type of network which is these days very extensively used, for instance, for recommender systems, for fake news detection, and so on. So there are a variety of applications where we observe signals defined on graphs, and so graph convolutional networks are the right way then to go. So these have a special, let's say, type of generalization. So in general, we discuss generalization as, let's say, one key property which we aim to understand for deep neural networks. Graph convolutional networks exhibit a certain type of generalization ability, which for others is not a question, because here we input also different types of graph in the neural network. And so it could be that the network only sees certain types of graphs, but other types of graphs which mimic the same phenomena are unseen, so that asks the question whether networks are able to generalize to those. Now, it doesn't solve the full generalization question, but I mean, it solves a part of it. And so there was a common belief that spectral graph convolutional networks do not exhibit this transferability property. We show here that this is actually not true, so they are transferable in a certain way. And what we show is we first of all define what it means that graphs exhibit the same phenomena by putting, let's say, a continuous space above, and then if different graphs are discretizations of this continuous space, then they exhibit the same phenomena. So we assume or hope that the convolutional neural network has on all those graphs then the same repercussion. And what we look at are spectral graph convolutional neural networks, a certain type coming from functional calculus. There we show that graph convolutional networks are transferable, and then we also show that, and so this is the estimate which we got. So filter transferability can be estimated by Laplacian transferability, and the consistency error being, let's say, this discretization procedure, how close it is to, let's say, the identity, and also Laplacian transferability can be estimated in certain cases. And with this, I would like to conclude and thank you very much for your attention.
Excellent. Thank you very much for that. That was excellent. We have a question in the Q&A pertaining to the reconstruction algorithms. Amber Paul asks, why is R1 not the same as R2? I am thinking of the reconstruction functions as a parameterized mapping from the space of graphs to the continuous space. Isn't the reconstruction process the same for both graphs?
Okay, so I assume he's referring to these R's, these R1, R2, I guess.
I believe so. Amber, you could feel free to correct us in the chat.
Yeah, so I mean, you see if, so you have the continuous signal here, I mean, then you go down on the graph. So this way you might already lose some information, yeah, because you discretize. Then if you go up, I mean, what you obtain then, even without any filtering, might be different, because if you have, in this case, you have a graph which just consists maybe of one point in each of these balls, and here you have a very fine discretization. I mean, then certainly if you go up again, I mean, you will lose a lot. So here you will get just a constant function on each of these balls. So in that sense, these are different, but also as a function, they are different, because R1 and R2, if I go back here, I mean, if these are different graphs, I mean, they're defined on two different domains. So therefore, I mean, the functions themselves will be different. So I hope I understood the question correctly. And
yeah, Amber confirmed that we interpreted correctly.
Okay.
Thank you for the answer.
Okay.
Next, I believe Renee has a number or a question or two. Please go ahead, take the floor.
Hi, Gitta. Thank you for a very, very nice talk. Very interesting and great as always.
Thank you.
So I have a very stupid question. I was really trying to understand the connection with what maybe would normally be understood by transferability within the machine learning context. And so I was grappling around, because if I think about generalization in machine learning, right, I'm trying to compare the gap between the expected loss and the training loss. And when I think of transfer, I'm typically thinking about, I've got a variety of multiple tasks, and I want to have the ability to transfer from one task to another task. And there is a lot of literature in transferability there. So when translating that to graphs, I thought, well, there's going to be some probability distribution on the space of graphs, and I'm going to have expected values of the loss of whatever training task I have. And the notions of transferability are different and pertain to specific filters. And so I was curious as to whether you could just put that within the context of the usual notions of generalization and transferability in learning, and how you could make connections, and whether there is a path of these notions of transferability having some effect on the more traditional notions of transferability.
Yeah, I mean, concerning, let's say, generalization, you see, I mean, the full question of generalization would be you would like to analyze the error if you have a very different, let's say, graph from your distribution. You input it in your neural network, and then you look at the outcome, and you compare to what you aim for, what your underlying distribution was. So here, I mean, we look at, let's say, we don't look at the distribution, we just look at single graphs. And so in that sense, I guess, I mean, if you now have a probability distribution on, let's say, your signals, yeah, I mean, first of all, I mean, as I said, I mean, it doesn't solve the full generalization question. It's just one aspect. So here, I mean, if you really want to look at it in the setting of generalization, you would need to take maybe a probability distribution. Just, yeah, but this also doesn't make that much sense. Yeah, so here, so what we compare is just, I mean, you have this continuous space and then you look at all possible discretizations of it. I think it's very different to if you now look at, let's say, a general probability distribution. I wouldn't see immediately how you can use it for getting insight, let's say, in the general distribution, in the common generalization ability.
Maybe if you could just re-explain your definition of transferability. I think in the paper, actually, you've got many possibilities.
Yeah.
And maybe why you call it transferability then, which can be confusing for those of us who are coming from the machine learning side.
Yeah, so these are, I mean, different settings which could be, let's say, seen in this framework. You have, let's say, you have a borrowed space, you have a sampled graph, and then you have these different, let's say, operation, sampling, interpolation, or you have a fine graph. So each time, I mean, you have an object where either this is a sampled object or it is somehow, let's say, a perturbed version. And then you're wondering how, let's say, the network acts on those and which error you obtain. Yeah, so, and I mean, as far as I know, I mean, the literature of graph convolutional networks, I mean, transferability was also used before our work. So in that sense, I mean, it is already not something, let's say, an expression we invented.
But isn't it in the end closer to the ability to, like in signal processing, the ability to reconstruct a signal from samples? So in a sense, you're doing a coarsening and then the measures are more of reconstruction error-like.
Yeah, but the point here is that in fact, I mean, what you want is, yeah, you see, I mean, so this is, I guess, the result you refer to. You compare everything to what happens on the continuous setting. But in fact, I mean, what you truly would like is this result. So you have these two different graphs and you would like to see how the network acts on those and what the difference is. I mean, the continuous setting is just to give a notion of what it means that two graphs exhibit the same phenomena. Yeah, so this just gives, let's say, a meaning to that and a meaning to when you would like that the network has the same repercussion. And so for those who fulfill this property, for those, then networks do generalize. So it gives us, in some sense, a class of graphs for which we can prove this generalization ability.
I have maybe a follow-up question with respect to that. Maybe in a particular example, say that you have some graph that is the discretization from a continuous problem. For instance, say that you want to do the max cut. So depending on, you train the graph neural network to solve max cut in a certain sizes of graphs, but then you want to say, since this is an approximation to a continuous problem where the Laplacian can do well, then you have this kind of generalization in that case. Mm-hmm. Right? Is that right? Mm-hmm. But isn't it a lower bound what you need? I got confused why the upper bound is the...
So the error you would like to, so what it tells you is you have, let's say, these two different graphs which mimic the same phenomena, how the network in some sense operate. Yeah, operating that. Yeah.
So it's an upper bound for the error.
And ideally you would like it to be equal to, I guess, even 0. Yeah.
And so your assumption is that the Laplacian, there is a spectral method that actually performs the task that you're learning for? Is there a dependency on the task that your graph neural network is training for? How does that show?
No. So, I mean, so what you need is that, I mean, so you have a ReLU convolutional neural networks with Lipschitz filters. So you are given this network, which I guess, I mean, certainly encodes a certain task. But the task in that sense doesn't really appear here. Yeah, so it's just that you have this ReLU neural network. I mean, we also don't consider, let's say, the training procedure or anything like this.
I see.
Yeah, so it's basically this built-in capability of spectral graph convolutional neural networks to, yeah, to how we call it, to transfer.
Okay. Thank you.
Great, thank you, Gitta. Are there any other questions from the panelists? All right, well, let's thank Gitta one more time. That was fantastic.